Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're revisiting the stuff that was broken in the recent NCC computer that I worked on the main channel. In a recent video, I worked on and repaired the Twinhead monochrome display adapter / Hercules / printer port. This thing threw me for a loop, and well, that was quite the repair video, so if you haven't watched that yet, you might want to check it out. Although, really that has nothing to do with this video because we're going to be taking a look at the floppy drive, the floppy drive that I said we were going to work on in the video where I did the repair for the video card, but I didn't get to it because, well, the video card was very broken. Well, it took me a long time to figure out what was wrong exactly. The floppy drive in question is a 5 1/4 inch, 360 kilobyte, double-sided, double-density disk drive with a nice black faceplate. Now these drives don't grow on trees anymore and they're getting much more expensive. So you might buy one of these or have one of these that doesn't work, just like this one. I don't know what's wrong with it yet, so I want to try to figure out what exactly is wrong with it to see if I can actually get this thing working again. Just like on the video where I worked on the Twinhead MDA card, there's no guarantee I'll be able to get this thing working because it might have a part that's failed that is completely irreplaceable. There are plenty of parts like that on this drive, but we'll only be able to figure that out if we do the diagnosis. So without further ado, let's get right to it. One of the issues you might run into while trying to troubleshoot and fix a disk drive like this is that the problems that these drives can be numerous. There's a myriad of things that can go wrong with them, including mechanical problems, electronics problems, a combination of both. Even bad disk media can be your issue, or your computer that you're trying to use for the testing and troubleshooting could also be faulty. Even the cable you use might be the problem. And one of the things I really try to recommend is that if possible, you have a known good floppy drive, known good disk, known good everything, so that you know that you aren't running into an issue with something else that's going to lead you down the garden path while trying to fix the potentially not working floppy drive. Another thing that's very important is you need to make sure that you know exactly the specs of the drive you're working on. So is this really a 360K drive, or maybe it's a 1.2 meg drive, or maybe it's a 720K drive, which is a double density drive, but 80 tracks versus 40 tracks. Is it 48 tracks per inch? Is it 96 tracks per inch? Is it 100 track per inch? Unlike with 3.5 inch discs, where you can be pretty much sure that if it doesn't have the little hole there, that it's a 720K or double density disc. If it does have the hole, that it's a 1.4 or high density disc. But with 5 1/4 inch media, you're not really so lucky. We happen to know this one is double-sided, double density just because the sticker says that. But if that sticker were missing, it would actually be really hard to tell what type of media you have. And if you try to use something like high density media in a double density drive, and there's a good chance that's not going to work, and there's nothing wrong with your disk or the drive, it's just incompatible media with the drive, and yeah, that's one of the other problems with these 5 1/4 inch discs. Well, since I found this drive inside a PCXT clone, then we can pretty much assume that this is going to be a 360K drive. It'd be extremely unlikely to find a 1.2 meg drive inside a PCXT, especially because there was no special disk controller that would be required to use that drive. This just was plugged into a very bog standard double density disk drive controller. So for testing my setup, I went and grabbed another 360K drive, and I'm quite sure that this one works. Ah yes, because I drew a tick mark on there. We have a Tandon TM65-2L. We can pretty much assume that the 2 means double-sided. It's possible there are single-sided variants of these drives as well, but we can see that there are 2 read-write heads, one on the bottom, one on the top, so we know this is a double-sided drive. And for me personally, when I test these, when I determine that it's a 360K drive and it doesn't work, then I'll put the capacity and a tick mark on the side, and if it's 1.2, I will write 1.2 and a tick mark, or if there's any other weird specialties about the drive, then I will write them right on the side so that there's no confusion in the future. So I'm just going to move the drive under test out of the way, and we're going to use this motherboard, which I was using to repair that video card in a recent video, to test this disk drive. And I keep this long cable around, which I'm pretty sure is going to work, but we're going to know for sure once I get this thing hooked up. And for regular IBM PCs, you need to make sure with your cable that you have a twist in there, because that determines if the drive is the A drive, which is after the twist, or no twist is the B drive. The other thing you have to consider is that on IBM PCs, you always set the drive to DS1. So DS0 is the equivalent of the first disk drive on the chain. It could be labeled DS1 on some disk drives. In that case, there is a DS1, 2, 3, and 4. But on this one, you can see that it's DS0 through 3. So we gotta set this to drive select 1. We also need to make sure if this is the only drive in the chain that it has a termination resistor, which this does. If this were not installed, this disk drive would not work at all. So we just need to connect up the cable, and this one happens to have the key, so you need to make sure it lines up with the notch on the drive. If your cable doesn't have that, it's not a big deal. You just need to make sure that pin 1 or the stripe is facing towards the key that is on the device, like that. Now this motherboard has a built-in floppy drive controller, and I've never actually tested it. So this is one of the reasons why I want to test this first, just to make sure everything is working with the controller on this motherboard before I go try to troubleshoot this disk drive and say there is a problem here. I don't want to blame the disk drive for a problem on the motherboard. Another thing that's really important to have, and this may be something that's hard to find, is you really should have a known good disk that's already formatted for the system under test. And we'll be testing these disk drives with an IBM PC, so this is MS-DOS formatted disk. And I've written this in another known good drive, so that way when I go to read this disk in both this disk drive but also that one, if I'm able to read the contents of this, then I know everything is working perfectly. If you don't have any known good formatted disks and you don't have any working PCs or working computers with known good disk drives, perhaps you can find someone locally in the Retro Computer Club or friends or whatever who could make a disk for you and confirm that the disk is good, so you can avoid any problems you might have with a disk that's written on a bad disk drive. Because say this disk drive that we're going to be testing in a moment has a misaligned head. The disk may format properly and read in the drive, but if you try to put this in another drive, it's not going to work. I've run into that problem before. Now, of course, it goes without saying, we need to plug power into the floppy drive as well. It's not going to work without that. And let's turn on the computer. Now, typically, if the heads have moved off their stop, and I'm just going to move them, as soon as you apply power, it should go back to the home position, which is the track 0. Okay, it didn't do that on this disk drive. That doesn't necessarily indicate a problem. That's just something that a lot of disk drives do. We did notice that it spun up briefly, and I think that was just the drive being powered up. Now, some disk drives, when you go to insert a disk, actually spins the spindle motor. And it looks like this drive is not one of those. Oh, it is. Okay, as soon as I lowered it, it actually started spinning the drive. Now on this Pentium motherboard, it does support 360K drives. Some newer PCs have floppy drive controllers that don't support these older type drives. That's not necessarily a problem, and if that's the case, you're just going to leave it as none. It just means you're not going to be able to use the disk drive in DOS. That's not to say you still can't test it with programs in DOS, ones that communicate directly to the disk controller, but if your motherboard does support the type of disk drive you're testing, like 360K, 5¼ inch, then select it. If this were a single-sided drive, you still would pick 360K, 5¼ inch. It'll still totally work. You just won't be able to use that second head. You can still read 180K disks and even format them in DOS. You just have to use specific parameters while you're doing that. And I think this particular BIOS, if it's working properly, because I don't know for sure, it should seek the disk drive. Once it finishes the RAM check, I'll just skip over that actually. There we go. So the head went back and forth. That's a good sign that this drive is working. So I did DRA. That's showing us this disk, which I formatted earlier, and I know it works. I did it in a different drive. And if you're not sure about that, and you're using a later version of MS-DOS, you can run ScanDisk, for instance. Oh, wow, it says it has a problem. Okay, well, I think that's a file system issue. That had to do probably with the way I originally formatted this disk, and I created it on a different computer. Anyways, one thing you can do with ScanDisk is we can do a surface scan. It's just going to scan the entire surface of this disk, and it's just going to verify that every sector is readable. What's great about ScanDisk is even if you have just MS-DOS 622 or any version of MS-DOS that has a tool like this, and then you can actually do this test. You don't need any special utilities. Now for me personally, if I have a 5¼ inch disk that has bad sectors, I don't like to keep those and use those, and that's just simply because I feel that once they get some bad sectors, they're generally failing anyways, and they can gum up your disk drives, but they can also start to have more and more bad sectors, and it's not like we're saving our special prize documentation on these disks, but nonetheless, it's kind of annoying when you go to use one of these disks in a system that say only has floppy drives, and it doesn't work because the disk is going bad. So typically, if I find disks that are bad, I will toss them out. The surface scan finished. That means this disk is working properly. In this disk drive, everything seems happy. So far, I've only been talking about testing this using an IBM PC, but not everyone has an IBM PC. Maybe you want to use one of these drives with a CPM machine or something else that uses the same Sugar interface. In that case, I highly, highly recommend buying one of these devices. This is a Greaseweazle version 4. There are a bunch of different versions of these, but they all work basically the same. This has a standard Sugar style floppy drive interface on it, and it connects to your host computer using USB. What is awesome about this particular tool is it's open source, so it's very inexpensive. You can make them yourself. There are constant new features being added, and the best thing about it is it's fully compatible with using disk drives on a Mac, Linux machines, and Windows computers. In fact, it probably works with phones as well. You can plug it into your Android phone and it would probably work as well, although I'm not 100% sure the utilities have been ported to it. The negative of a device like this is it's a little bit harder to use than just plugging a floppy drive like we just did into a PC, simply because it uses a command line interface, so it's a little bit harder to figure out all the right syntax to do everything you want to do. But when you do figure it out, you can use this device to great effect, not only testing disk drives, but formatting disks, reading disks, making disk images, even writing disk images. And the best thing about it is you can use this on a modern computer to make disks for other platforms that you normally couldn't write to. For instance, you can make Apple II disks with this, or Commodore disks with this, or CP/M disks with this. All sorts of different things are possible with these. And I'm planning to make a video in the future just showing off like some of the scripts that I use to facilitate all of that. But in this video, I'm only going to be touching briefly on this, and I plan to use this to actually do some testing on the broken disk drive. It just depends on the obstacles we run into when I do hook that up to the PC, because sometimes there are situations where the PC really struggles to talk to a disk drive because it's, say, running way out of spec, and the Greaseweazle can actually help with those types of things. And incidentally, the cable and the power supply I'd be using to run the disk drive is the same. If I was going to be using the Greaseweazle, I'd just unplug this cable from the motherboard, plug it into this, plug the USB into my computer, and I'm off to the races. At this point though, we know this disk is working, we know the cable's working, and we know the motherboard works as well. So now's a perfect time to unplug everything from this tandem working disk drive. So let's take a look at the faulty disk drive. Last time I tested this, I just figured out that it wasn't working, and I wrote slow question mark because it just sounded slow to me, but I didn't do any further testing. So this particular drive is around roughly from 1988, and that's when it was installed in that computer at least. And one thing you might recall from the NCC repair video is that the entire computer had this nicotine glaze all over it, which is actually tar. A lot of people put that in the comments, and I know that's the case, but there's quite a bit of it on the disk drive as well. In fact, let's just get a little cloth here with a little bit of Windex on it, and I'm curious, yep, that's it, that's that glaze. Well, one of the issues is that's going to get all over the inside of this drive as well, say on the heads, on all the sensors, and that can cause operational problems as well. Not to mention the drive smells a little bit, although I found with the PC after I did a little bit of cleaning and washing, it didn't smell so bad anymore. Now I looked through my stock of disk drives and I wanted to find the same model if I had the same model in stock, and that would just allow us to compare parts, or maybe if something were bad on this I could swap things around. And when I looked through my parts, I did not find another drive like this. So this is actually a Fujitsu drive M2551A 26B with its long serial number, made in Japan. There's a few key points. This thing has a termination resistor pack installed, so that's good, we needed that. And it's also set to drive select 1, just like I said it needs to be for working with the PC. Let's get this metal cover off the drive. I think I took this off the drive during the teardown on the repair video for the NCC computer, just to take a quick gander under there. In fact, yes, I did obviously, because I wrote 360 with an X on there. Pretty sure that was me who did that. Now with the cover off, you can get a good look at the read-write heads. And as I mentioned, that tar buildup could be on those heads, which obviously would cause it not to be able to read disks. When you look at the floppy drive, there's also a hole there that's for the index sensor, and as the disk spins, it's able to read that, and that would be the top part of the sensor. There's an infrared LED that shines through the hole, and there will be a sensor on one of the sides that is able to sense that light. So as the disk spins, it's able to know the exact RPM of the disk spinning. Whoa! A little bug just came out of there and kind of freaked me out. As I was saying, as the disk spins, it breaks the beam, and as the beam is shining through, then it's able to sense the exact speed of the disk. Typically, on most disk drives, that signal is not used for speed control for the actual rotational RPM. That is simply relayed through the connector to the host computer, so the host computer is able to know how fast the disk is running exactly. The same thing exists for the write protect sensor. Currently, the LED is shining down onto the sensor. It is able to see the light. But when we stick the disk in there, it actually blocks the beam, and that's one way that the drive knows that a disk got inserted, and that's how it might start spinning the spindle. And obviously when the disk is pushed all the way in, then the beam is now able to pass again because this disk has the notch cut in it, which allows the disk to be written. Putting a sticker over this blocks the beam, which actually gates the controller to prevent it from writing to a disk, so it actually physically can't write to the disk. There's also a signal that passes through to the host computer through the connector. Now the index sensor, on the other hand, is required by most computers that use this style of interface. So if you take this disk out and you flip it over, well, obviously the hole's on the wrong side now, which means there will be no index pulse, and most computers are going to complain that it can't see the index pulse and it's going to refuse to read the disk. There are plenty of computers with disk drives that don't use a SugarArt style interface, that don't rely on the index sensor. And Apple IIs and Commodores come to mind, and I'm pretty sure Ataris also don't use the index sensor. That means you can flip the disks over if you just cut a notch for the write protect hole and use both sides of the disk if it's a single-sided drive. Now, as I mentioned, the heads could be dirty on this, or some of the sensors could be dirty, so you might want to use something like a clean disk. These are getting very hard to find though, and very expensive. So what you can also do is just use a little cotton bud with a little 99% IPA and very carefully clean the read-write heads. If you are trying to clean these, you have to be extremely careful lifting the read-write head. The amount of pressure that this exerts onto the disk and the bottom head is critical for the reading of the disk. And the entire spring setup here is calibrated at the factory to exert the right amount of pressure. And if you do lift this by hand, you have to be very careful just to lift it just enough to get the cotton bud in there. Now you may notice that the read-write head on the bottom, that's the white thing with that black line in it, is mounted on what looks like a gimbal. It's not really a gimbal, it's just a piece of stamped metal. I'll just demonstrate it by poking it ever so slightly. So you see how the whole thing moves? So you just have to be very careful when you're cleaning that to not damage that entire structure. The top head also is often on something very similar. So again, cleaning these, you just have to be super careful. A lot of times when it's a single-sided drive, the top side only has a little pad, a felt pad that pushes on the disk, because that pressure is still required for it to read the disks. But the bottom head on those drives is typically physically mounted. It doesn't move around. Well, it moves on the sliders, but there's no little gimbal there, so it's a little easier to clean. Although, again, the whole pressure with the spring on the top is still very important, as is that felt pad. So the thing about these cleaning disks is they just make it really easy. You just don't have to worry about that. You just put a bunch of 99% IPA on there and initiate something to get the drive spinning, and that typically has the effect of cleaning the drive. And that's what I'm going to be doing in this video. Okay, enough talking. Let's get this drive powered up. Let's see exactly what this is doing when I try to, well, clean it and read this disk. So before I power up the drive, I'm just going to move the head assembly, and I'm going to grab it at the base there so I'm not touching or pulling on the actual heads. And I'm noticing this moves very freely. I can't remember what I did exactly in the NCC video where I tried to get this drive working, but I think I might have dropped a few bits of bearing oil onto the sliders just to get that moving smoothly. If the heads aren't moving, typically what's going to happen is you're going to try to read, or you'll power up the PC and try to seek the heads, and they'll just kind of be stuck. If that happens, there's a good chance that the sliders are gummed up and you need to lubricate them. But the other thing that can happen is the stepper motor. If we flip this over, this is the stepper motor that moves the heads. This could be physically damaged, or the control signals that go to this from the main board also could be faulty, so it won't step properly. There are a myriad of issues that could go wrong with these drives. As I mentioned, that's because there's so much mechanical stuff happening here. I'm going to move these heads all the way towards the spindle. Track 0 is all the way toward the back of the drive. Let's power up the computer and see if the heads move on their own on this drive. Okay, they don't, but they moved a little bit. Now when the computer adds its boot, it should try to seek the heads. We should see that in a moment. Yeah, okay, so just like the other drive, it ended up back at track 0, which is correct. So we're going to use this cleaning floppy, and I've used this a whole lot of times, and it says you're only supposed to use it 15 times. I probably used it 100 times by now, and that's just ridiculous. You can use these plenty of times. I assume if they get super filthy, that's maybe when you want to stop using them, but at this point, this thing is fine. So I'm going to pop this in, and now we just need the drive to spin a little bit. So we just look at the A drive, and there it goes. Now, remember on my label I wrote slow. I'm used to the way that this cleaning disk sounds while it's inside a disk drive, and that does not sound right. It sounds like it's running too slowly right now. And that really just comes from my experience of working on a lot of these disk drives. For pretty much every single computer that uses a SugarArt style drive, which is what this is, it should run at 300 RPM for double density disks. And it sounds like this is running slower than that. So what I just did is I popped in my known good disk, the one we tested on the other disk drive. Let's hit retry. Oh yeah, it's running way too slow. I could just hear it. It just sounds like it's running at the wrong speed. Now for working on floppy drives on IBM PCs, I really highly recommend this program, ImageDIsk by Dave Dunfield. This version 1.19 is widely available. It came out in 2022, so it's pretty recent. And what's cool about this program is it talks directly to the disk controller on your motherboard. So even if you don't have ability to set the BIOS to say 360K floppy drives, it doesn't matter with this utility. It overrides whatever the BIOS is doing and talks directly to the controller. And that's why when you run this program, it currently thinks we have an 80-track drive. You'll go over on the right, but this is actually a 40-track drive. So you have to hit S for setup. We're going to keep it on A drive because that's what this drive is. We'll change it to 40 tracks because that's what this is. And this is a two-sided drive, and the double step needs to be off. Generally, the double step feature is only used on 80-track drives, like a double density drive. If you're trying to read 40-track disks, what needs to happen is the heads have to step twice for every track on a 40-track disk when you have it in an 80-track drive. Again, these are the weird idiosyncrasies of 5¼ disk drives, because there are all these different formats with different track per inch, stuff like that. But a 360K drive like this is a normal 48 track per inch drive with 40 tracks, two-sided, and that's pretty much all you have to worry about when you're setting it up in here. Now, one of the things we can do is we can hit A for align. And what this is going to do is it's going to try to read sectors off the disk. And let's hit enter and see what happens. So the first thing it does is it tries to figure out what bit rate the drive is running at. Double density is always running at 250 kilobits per second. And if this can't figure that out, okay, it settled on 250 double density, which is correct, but it's not reading anything. So all question marks. Even though the drive is spinning, the computer or the controller is just not getting any useful data out of it. Oh, we're getting like a tiny bit of reads out of it. Whoa. Wait a second, so it just started working? Just randomly? I'm gonna hit B to turn the beep off. That is kind of ridiculous. I didn't do anything, you saw it, it just started magically working. Now, every track on a 360K IBM PC formatted disk has 9 sectors per track. And when the IMD align program is used, it's going to report 18 when it's reading all 9 of those tracks. I don't know why it reads double like that, but that's just the way it works. Now, at the very top, you can see it says track 0, head 0. So I can hit H to switch to head 1. So now it's reading the other side of the disk. If this top head weren't working, like I can actually lift it slightly. Let's just do that. So there we go. It lost the ability to be able to read when I lift this up. Now, it would also lose it on head 0 as well. So now we're reading the bottom side of the disk. If I lift this top head, it'll also lose the ability to read. And that's because that pressure is required to push the disk into the head. And that's that spring pressure. Otherwise, it's just not going to read anything. Now, one thing that's very helpful with this is we can push numbers like 3 to jump to track 30. Let's just do that. And it's just reading now. Why? I don't know why. This doesn't make any sense. And now I jump to track 40, which is actually track 41, because the track numbers start at 0 in here, even though when we were setting up the disk drive, we said it was a 40-track drive because the first track was 1. A little confusing how it's a little bit different, but typically we call this a 40-track drive, but in reading the disk, track 39 is the top track. So if I hit the minus key, it's going to go back to 39, and now it's actually reading track 39. Now, one thing I have to mention is that the format of the floppy disk actually encodes in the sector what track the sector is located on. So sectors on the 39th track say 39 in them. And that means that a program like this, if the head is misaligned and it's reading a different track, the program thinks you're on track 39, but it's going to be reading sectors from a different track, and it will be able to figure that out. So I'm just going to force the heads to move a little bit. Got to do this carefully where I don't break anything, but there we go. So now notice it says 29. So we're on track 29, but notice how the 18 moved from the middle over to the far right, and that's because it's reading 18 sectors. Now if I turn on the beep will be at a different frequency as well. Let me hit R, which recalibrates it. Okay, now it's high-pitched. And that's because this program is able to tell, hey, I'm reading sectors correctly, but I'm reading them off the wrong track. So that's really good for knowing if the drive is out of alignment. And if you do try to manually align a drive, this utility is relatively helpful for this specific purpose. And it's normal when you change tracks to have a couple sectors that are missed. So notice how it went from 18 to 12 to 14. That's totally normal, and that's because, of course, the disk is spinning and the heads are moving while the disk is still spinning. So, of course, it's going to like miss some sectors or whatever in that transition period, but it just needs to settle back on 18 very quickly. Now, I just want to throw out a little extra tidbit here that if you're trying to read a disk that's 5¼ inch, it's physically compatible with this drive, and it's not written in an MFM or an FM format, frequency modulation that's single density, or MFM that's double density, then the disk controller on an IBM PC is not able to read those disks. So I can't stick an Apple II disk in here or Commodore disk in here and have this IMD program actually work. There are tons and tons of computers out there that do use a SugarArt style drive like this and an MFM or FM encoding, and IMD will be able to read those. TRS-80 Model 1, lots of CPM machines, just all sorts of stuff uses that type of format. It may have a different number than 18, it might say 30, it might say 9, I mean, who knows, it can be all over the place because the sectors per track is not fixed on these disks, they're soft sectored. But for normal IBM PC formatted disks, it's always going to show 18 like it's doing here. Now I'm still thrown for a loop a little bit that this thing is just magically working, and that kind of sucks because the repair video I was going to try to make is not going to be anything. We have nothing to fix, theoretically. Maybe this thing will break again, I don't know. So exiting out of the alignment program, one of the things we can do is we can do test RPM. And this is one of the negatives about IMD, is it can only test the RPM of a drive if the disk is readable. If the drive is running too slow or too fast so it's not really readable, then this thing actually fails. And I'm pretty sure in the NCC video where I first tested this drive, I tried to run this test and it did not work. But we can see here that we're running at 300 RPM or 301 RPM. It averages as it sits here and reads it for more and more. But I have no clue whatsoever why this thing just magically started working. And I'm really glad that we got it on camera. I'm recording, right? Yes, I am recording. Otherwise, people might not have believed me. This drive was definitely not working, and then poof, it's working. Now, I recently picked up this digital tachometer, and it was very inexpensive, and I wanted to give this a try to see if we could read the actual RPM off this drive. The one caveat is this needs a little reflective piece of tape installed onto whatever's spinning, and the device came with these little retroreflective strips, and I'll stick that on the drive. Now, this may not work because this is too shiny already with the metal texture. So what we'll do on here is we'll run the alignment mode, because that just seems to run forever, and let's see if the drive can actually read anything. Oh, it's still working. Okay. And we can see that this is not quite working. 800 RPM, 1500 RPM. Uh-oh. Something's weird. I think it's slowed down. Oh yeah, look at that. We actually had a period where it wasn't reading. Okay, well I think to make this thing work, I'd have to put a black sticker or black marker or black paint all over the spindle so that the little shiny part would have something to reflect off of. So we're gonna ignore that for now and go back to what this thing was doing when I was flipping it around. It seemed like it was having an issue. Now the drive's actually been sitting here for a few hours. I went and had dinner and whatnot, and it has been turned on. The whole computer's been left on, but I'm curious if it has re-broken again. Nope, it's working. There's the beeping sounding normal. So I have to admit, that kind of ruins my video. I thought this was going to be a repair. Oh. Okay. It has re-broken. And it's not like it's rubbing on the desk because I'm lifting it up. It's definitely slowed down. And it's back. What is going on? Now, I thought if there'd be a mechanical issue, say with the bearings, you'd hear chattering or dragging or some kind of noise. But no. All right, well, what we need to do is we need to figure out if the RPM is really slowing down or what's happening exactly. So I'm gonna go back to test RPM. Now the problem with this is the speed is averaged. So there's that 300 RPM at the top. Now the interesting thing is I am adding a lot of drag to the motor, but these types of speed controllers can compensate for extra drag. Some discs are harder to turn than others. And even with my finger rubbing on it, it's still running at 300 RPM. So that means there's plenty of torque in the motor. So I sort of feel like maybe we have a bad connection on here. So let me fiddle with these wires. You know what? I should probably go back to alignment mode because we can see visual feedback if it messes up. In fact, I can turn on the beeping. So I'm just gonna move the wires around. See if it starts misbehaving. Touching everything, seems fine. This is the connection that goes from the main controller board to the spindle motor controller, a speed controller. That chip is pretty warm. Could it be these caps? I mean, poking at this board doesn't seem to have any effect. And obviously, if I drag my finger on this, it's still reading fine. Okay, well, I had a little bit of an issue there, but I really put a lot of drag on it. So I'm going to put a lot of drag on the motor, slow it way down. So there we're getting the question marks. Because the drive seems stable, but we saw it mess up multiple times there. Now it's working fine. Banging it on the table, that doesn't cause any issues. This is kind of like the problem that you have with your car, and then you take it to the mechanic and you're like, it's doing this XYZ, it's not working, and the mechanic can't replicate it. And honestly, if they can't replicate the problem, it's very difficult to fix. And that seems to be exactly what's going on here. Now, when it comes to the actual speed control of drives like this, you might be looking at this little adjustment here and think, oh, maybe that's the speed control. It's definitely not. This has to do with the differential amplifiers for the read-write heads, so I would never adjust that unless you know exactly what you're doing. I'm just hoping that by moving some components around, that I'll bring the problem back. But that is not happening. Not even a little bit. Well, I suppose there's one thing we can do. Let's exit out of here and let's try to run ScanDisk on this floppy like we did with the other disk drive. Let's see if it does a full surface scan of the drive or the disk without any issues. Drive is nice and quiet. ScanDisk did not find any problems on the drive. Of course it didn't. Well, I just shut the power off. I'm not quite sure where to go from here. I suppose I should probably let this thing cool down for several hours or maybe overnight and see if the problem comes back. The only thing I can think of is there's some kind of an issue on the speed controller board with these tiny little capacitors. It doesn't appear that we have any kind of leakage or evidence of problems, and they're not surface mount caps, so there shouldn't be a problem there. Now, one of the issues with trying to replace these capacitors is you have to take apart the entire spindle mechanism to even get this board out of the disk drive. And there's the Write Protect, probably LED or sensor. That's right there. It actually has a diode indication, so that would be the LED. And frankly, I'm not exactly sure if it's a good idea to remove this board. So if I was going to try to swap these caps out, I might actually just rip these off the board and then use the legs that were left behind to solder the new capacitors in place. Actually, you know, I just had a thought. I want to run this drive, and I have some freeze spray. I'm going to hit the bottom board with some freeze spray, the IC, and those caps. Let's just see if that behavior comes back. Here's some of my freeze spray. Generation 2000 Arctic Air 2 Zero Ozone Depletion Write-Off. That's an odd company name, Write-Off. Whoa. It's doing it right now. I can tell it's running much slower than normal. And it's making a weird sound as well. Whoa. Whoa, did you see that? How like it kind of stopped and then started? This has got to be a problem with this controller IC. It's just got to be. Now, these little contact pads here, we should be able to scope and see the waveform going into this motor. It's a 3-phase motor. Let's get this tab broken off. Wow, this is an old product. Someone gave this stuff to me. I don't know what year this is from. It's probably from the 90s. All that this freeze spray is the same thing as this compressed air duster stuff, which I don't really use much of anymore because I have one of these little battery-powered ones that works quite well. And my assumption is that these have a tube that goes to the bottom, so it picks up the liquid on the bottom no matter what. Either way, let's just test this. Oh yeah. Oh, that's cold, all right. Okay, I'm gonna turn on the beeping, so sorry about the annoyance. And I'm gonna drizzle this on. I mean, nothing's happening. And it's freezing cold, that chip. Very interesting. I kind of would have assumed that the IC, maybe when it was cold, would start to misbehave, kind of like it did when we first powered it up. But that doesn't seem to be the case. Oh, it's doing it right now. Do you see how slow the spindle got there? And I could hear kind of a humming noise coming out of it while it was doing it. Not like it was a mechanical bearing problem, but just like the drive signature got kind of out of whack. Well, let's hope this misbehaves. I have the red trace set to 5 volt per division. Let's take a look at these signals. All right, so there's one of our waveforms. If I slow the motor down, notice the amplitude increases, I guess, as it tries to apply more torque to the motor, but the frequency is pretty stationary. 50 hertz, according to the frequency counter there on the scope program. I'm now probing the middle of the 3 test points. Waveform looks the same. Yep, looks fine. Now I'm on the rightmost one. They all look essentially the same. But if I grab another probe, what should be happening is these three waveforms should not be overlapping exactly. They're all out of phase with each other, and that's what creates the motion of the drive. So now what we need to have happen is the drive needs to mess up so we can take a look at the waveforms. All right, and I found another signal. This is on one of the inductors that's near the IC. Let's see if this has a waveform, 803 kilohertz. I wonder if this is like a tachometer signal. Nope, slowing it down doesn't really change anything. So this must be like a clock signal perhaps that runs this IC. In fact, this little green package says Y something or other next to it. So maybe this is actually a small crystal oscillator. And this is what this chip runs off of. That makes a bit more sense. Now there's this signal as well on one of the resistors. It's actually my assumption that this is a speed correction signal. So these pulses may indicate speed correction in a positive or negative direction, which is why when I slow it down manually, all the pulses move down to the lower side. And the width of the pulse indicates how much correction needs to be applied. So I'm dragging the motor right now and it's needing to apply a lot of speed correction. But when it's running at the 300 RPM, the speed correction, positive and minus, is minor. And zooming out a little bit, you can kind of see that, but if I slow it down manually, it all moves to the negative side. So I think ultimately what we need to have this thing do is mess up a little bit, and then we should be able to see these waveforms go bad. But everything has been working just fine. Let's see if we take the disk out, if the drive signature changes at all. Oh, it goes down, which I assume is because there's no more drag. Yeah, the amplitude goes down. So the spindle is still spinning. Sorry, you can just see it there. But the amplitude is less now because the disk itself presents quite a bit of drag on the motor. And again, that must be that speed control signal that we saw with the little pulses, positive or minus. So it probably goes over speed and then it reduces the drive to the actual motor because there's too many pulses on the top side. So it, tries to slow down. All right, so I grabbed another oscilloscope probe. This is only 2-channel scope, so we can't look at all 3 of these channels together. There's one of the channels, and there's the other channel. So you can see they're out of phase, and we can pretty much assume that that third phase, which I'll just probe right now, there it is. So that is just to the left of the red trace, and when I do the middle one, it is just to the right. So that pretty much confirms exactly like I thought, just a 3-phase induction motor. Well, what we need this thing to do is mess up, and it hasn't done that at all. So I think I'm just going to turn the computer off and step away and have the scope ready and power this thing back on after this thing is all cooled down a while and see if this problem came back, and so we could see the waveform with it misbehaving. It's the next day. I've had some time to sleep on this problem, think about it a little bit, and hopefully the drive has done whatever it needs to do, cooled off or rested, so that when we power this up, it is not working. I am concerned that if the drive is misbehaving, that it will just fix itself like it did yesterday, which will make troubleshooting this thing that much more impossible. Now, I've already edited up the footage I took from yesterday, and I was able to confirm that the camera captured the motor changing speed and slowing down. Hopefully that will be obvious when you're watching it, that you could actually see that the motor was having trouble spinning. So I wanted to start today's diagnostic session armed with information about what possibly could be causing the motor to not turn properly. So I've written them down on this post-it note. I'm going to reveal them one by one. One of the things about this chip is that it receives a motor on-off signal from the controller on the other side of the disk drive. That's the one that moves the heads around and does the read-write and all that stuff. Well, what if that on-off signal isn't making its way through to this chip properly? Maybe there's a bad connection. Maybe the driver on the other side coming out of that large IC isn't sending the correct signal. I never scoped the signal coming over this cable. I did just move the cable around just to make sure that it wasn't a loose connection, and it definitely seemed like it wasn't. Now, when we look at these 4 pins, we know that there's going to be 12 volts, ground. There's also going to be the motor on signal, and then there's one more wire. You might be wondering what that's for. Well, that's going to be for the Write Protect LED to power it up. This is an infrared LED that shines up through the disk to the sensor on the top side of the drive. And we can actually see that it looks like there's a trace that goes to that resistor and probably connects up to these wires. The connection from the LED seems to make its way to this resistor. On the other side of the resistor, where it's labeled 5, probably for 5 volts, almost certainly makes its way to one of these pins. There we go, it's that one right there. It's the black wire. Now the other connection that's labeled plus It's almost certainly going to be 12 volts. Let's see if that's correct. Yes, it is. 0 ohms. So we have 12 volts. We have a signal that goes to the LED. We're almost certainly going to have a ground signal, which I'm assuming is going to be that wire. Nothing is really exposed on the top of the board. There must be traces on the other side. And the connector for this must be maybe surface mount on the bottom side as well. Surely we can find the ground on some of these resistors though, and there it is right there. Probably on the IC. Yep, there we go, those pins are grounded. So the last signal is the C signal, and this is going to be the control signal. Let's see which wire it is. It's the blue wire, and that's the signal that actually instructs this motor to start spinning. Well, it's probably a good idea for us to figure out which pin on the IC is the motor on signal and just take a look at that and make sure that it's getting through correctly. And probably one of these is going to be found on the controller here, although there's maybe a resistor in between. Nope, no resistor. It's right there. So that's pin 22. All right, so the next thing is when the drive is malfunctioning, we need to take a look at those waveforms. We looked at them yesterday in that footage. That was the 3-phase waveform that drives this motor. Well, we need to know if those look good while it's messing up. It's possible that there's something failing inside this chip maybe, and it's not driving the motor correctly. It is interesting how it comes and goes because whatever fault is happening, it's obviously intermittent, and is there a bad connection inside there or a bad connection on the board, something like that? We'll have to do a little bit of figuring that out. It might mean I have to take this whole board off and we have to look at the other side to inspect it. Next thing is the clock input to the IC. This is the 800 kilohertz crystal or oscillator or whatever this is, and that feeds this main IC for its operation, and maybe the clock is failing. And while it's failing, this thing is not working. We saw the clock signal on one of these components. I think it was maybe the capacitor up at the top there, and maybe we need to take a look at that while it's malfunctioning just to see if we were seeing the 800 kilohertz. Next up is the Hall effect input into the main IC. These ICs work with Hall effect sensors under the spinning disc. There's some magnets under there. Maybe one of those signals is messed up, and we'll need to take a look at the data sheet for this to see how those signals should look and maybe figure out which pins that it's connected to so we can scope those if it's malfunctioning. Perhaps that feedback signal with the Hall effect sensors is messing up somehow, and that is creating the speed problem. I wrote caps on here because we do have these electrolytics. There are 3 of them. Thing is, I don't think it's that. I don't see how caps could cause a problem to come and go so intermittently like is happening here. If it happened a little bit and then completely went away, sure. But the problem yesterday kept coming and going, and that just is not indicative of a capacitor issue to me. And the last thing on the list is bad solder joints. Maybe there just is a bad connection here, and of course a bad connection could cause any of these things to stop working, like the Hall effect feedback might stop working, the clock might stop working. All sorts of things could happen from bad solder joints, and we really can't see anything on the top side. We'll have to take this thing apart entirely to look underneath the board and check those connections. Now, I don't really know how to get this apart. I would just imagine taking these 3 screws out and maybe this comes off. And underneath this cover, which has a permanent magnet around the outside, there should be some screws that allows me to take the PCB off. So hopefully this can come off without too much difficulty so we can properly inspect underneath the board. Now yesterday, I identified that these 3 connections are the waveform output from the IC that goes to the induction motor, and we were using the oscilloscope just 2 channels at a time to look at those waveforms. Well, in order to scope all 3 of those signals at the same time, I decided to break out my old Rigol 1054Z. Haven't used this thing in a while, but it's a 4-channel scope, and I think I can hook this up to all 3 of those, plus maybe the motor signal or the clock or one of the other signals on here, so we can probe around while this is malfunctioning to hopefully figure out exactly what's causing the issue. Now, I do have one concern, is that I will need to solder some wires onto these 3 phases in order to hook the oscilloscope up, and I worry that me trying to solder onto these with little wires might actually cause the problem to go away. And that's because if the issue on my list was something like bad solder joints, well, heating up the board, that could potentially fix the issue. And I don't want to just fix the issue. I want to be able to see the problem first before I do any kind of fixing. Now, I did a quick Google search and I did find the data sheet for the IC that's on here. It's a facsimile copy of a copy of a copy, but it's good enough for us to see what it's doing. So this chip is a semiconductor integrated circuit designed for single chip controller for a floppy drive spindle motor, consisting of a power amplifier, Hall amplifier, FG amplifier, oscillator, and speed discriminator, and various protection circuits. The device shows superiority in speed switching functions of 1 to 1.2, which enables miniaturization of motor sets and cost reduction. Now what's it talking about with 1 to 1.2? That is talking about 300 RPM or 360 RPM operation. I mentioned earlier that 5¼ disk drives always run, or almost always run, at 300 RPM. The exception to that are 1.2 megabyte high density drives. Those run at 360 RPM. And the reason for that is a 1.2 megabyte high density 5¼ inch floppy drive is just a miniaturized version of the 8-inch disk drive standard. 8-inch disk drives typically have 77 tracks or 80 tracks. They could be single or double-sided, and they run at 360 RPM. On any computer you have that uses an 8-inch disk drive, you can substitute a 5¼ inch high-density disk drive in place of the 8-inch disk drive, and it will just work. 8-inch disk drives run at 360 RPMs, so to enable that miniaturization, IBM decided to make 5¼ inch disk drives also run at 360 RPM, breaking the standard that had been established for many years where they run at 300 RPM. So controllers like this typically have an extra input on them to enable switching between 300 RPM and 360 RPM. A lot of high-density 1.2 meg disk drives are dual speed. I know I've talked about this in the past in some of my drive testing videos. Typically, those drives that allow dual speed operation will have an extra wire running to the underside where the speed controller is, and it goes into this IC and it will switch the speed of the operation between those two speeds. If it's a single speed drive, it might use the same chip. It just fixes that input to low or high, whichever it is, to operate at 360 RPM or 300 RPM like this drive. Now for recommended operating conditions, one thing that stuck out is the recommended frequency for the oscillator is 400 to 650 kilohertz. Without a doubt, this part here is labeled as 800. This is an 800 kilohertz part. So I guess Fujitsu, when they made this drive, they decided that that was an appropriate oscillator, even if it goes beyond the recommendations for the manufacturer of this IC. Now looking at the block diagram, we can kind of see what's going on. We have the output phases that go to the motor. Those are the 3 phases. We have the Hall effect inputs that would come from the sensor so it knows that the motor's operating at the correct speed. We have the 2 enable inputs, so either enable low or enable high. Oddly, those go into pin 24 and 31, but I wrote on my post-it note that it seemed that the input from the top board was going into pin 22, which looks like that has to do with the error amplifier, which would be a speed control function. Oh, I can see why. There are 2 versions of this chip. There's a P version and an SP version. This is the SP version. And on the SP version, pin 22 is the enable pin, which matches exactly what we found with that signal coming from the top board. So the block diagrams for the P version, that means the pin numbers don't match. So no big deal. I'm sure the functions are all exactly the same. Now looking back at the functions on the block diagram, at least, we have the oscillator input and the discriminator. This has to do with the speed control, obviously. From an electrical characteristic standpoint, the enable signal needs to be higher than 2.5 volts. So that's what I've written on here for us to look at. Incidentally, it's pin 30 that is the speed select signal for 1.2 times speed or 360 RPM or 300 RPM. Now this datasheet has waveforms. Take a look at this. There are the output waveforms for the drive signatures, and it matches exactly what we were seeing on the oscilloscope. And there are the Hall effect waveforms, at least from a timing perspective. Now we go back to the block diagram. Notice that it uses the differential amplifiers for the Hall effect sensors, and that means we may not just be able to scope those. Pretty sure this is what we were looking at yesterday when it came to those pulses that were high or low to try to get the motor to speed up or slow down. So pulses that go above the reference voltage are deceleration pulses, and the pulses that drop below the reference voltage are the acceleration pulses. That matches exactly what we saw when I dragged the motor with my fingers. All the pulses went down below and they got bigger, and that's the acceleration pulse trying to speed the motor up. When the motor was operating correctly, those signals looked perfect and they match what we see in the datasheet here. Well, I think I've learned pretty much everything there is to learn about the operation of this drive. I think the next step is we need to take this spindle apart so that we can see if there are any bad physical connections under there or any other kind of damage. And this is where I am going into uncharted territory, and that's because I have no idea what I'm doing. So let's see if we can get this out. There we go. That was in there pretty tightly and no Loctite. Need to make sure not to lose those. Oh boy. Well, that just stripped out. Great. Come on, really? I mean, this bit's making really good contact. I wonder if these are JIS screws and not just normal Phillips. And this is one of the reasons why I recommend not trying to take stuff like this apart, because these screws have been in there a very long time, and I'm not sure how I could have used a better bit than this one, which seems to have fit perfectly. And now I have 2 stripped out screws. Well, that got medieval. I had to drill those screws out. They were just completely stuck in there. But with them out, I can lift this off now. There it is. Now we can get a look at this induction motor. So this black ring around the edge, this is the permanent magnet, or the permanent magnets, plural, on this disc. And the 3 phases this produces energizes these coils in a way that gets this spinning. And I don't really understand how this kind of stuff works. It's a little bit of magic to me, but I guess these traces that run around the edges, maybe this has something to do with the Hall effect sensor. What's wild is even after drilling out those screws, those are still stuck in there. So it wasn't stuck because it was over torqued. I think it was stuck because this metal, maybe it's brass, and whatever these screws are made out of somehow fused together. Well, I'm gonna keep disassembling this. I'm just gonna take out this 3 screws that are holding on the coil, or whatever, this thing. At least these ones come out easily enough. And indeed, I can now lift off the entire PCB. Okay, well, what we see under here, besides a bunch of smuts from the cigarette smoke, there's the LED for the index sensor, there's the LED for the write protect sensor. And is that a little bit of corrosion around there? We can see all the various connections from the leads that run from the main controller and all the other components. I'm pretty curious what this stuff is around here. This does look like corrosion. How interesting. Which makes me wonder, these are the 2 caps. I guess those maybe did leak. Because look at this, yeah. All the solder resist is coming right off. Very indicative of leaking caps. I'm just trying to be careful handling this because the coils are loose now and I don't want to break the connections they're soldered on right there. I should probably get some tape and just tape over this stuff. Just gonna tape this on like so. That should be fine. Yep, okay. Now the corrosion that we see on the board that I'm scraping, this is the ground plane. So it doesn't seem like it's a signal wire specifically. I've written down the 3 capacitor values and their locations. I'm just gonna remove these from the board. Let's see if they test okay. There are the 3 caps. They don't look like they've leaked. And sniffing them, they just smell like cigarette smoke. I can't really smell the fishy smell. Does that maybe look like there's some leakage, or is that just residue from the cleanup process? That might be residue from the cleanup process because it looks like it's all around over here as well. All right, we have some new capacitors to install. So 468 nanofarads, 0.47 microfarads. It's 10 ohm ESR, but don't let that fool you. That's a 50 volt cap, so that's pretty typical. Let me find the one I took out of the board. There it is. 466 nanofarads, 12 ohms. So really, basically the same. Next up is the one I took off the board. It's 16 volts, 22 microfarads. We're getting 19.7 microfarads, 2.6 ohm ESR. Now it's at 1 kilohertz. The closest I could find is 22 microfarads at 25 volts. So 2.5, 18 microfarads at 1 kilohertz. So basically the same as well. So this is the brand new 0.1 microfarad, 50 volts. So 96 nanofarads, that's correct. 76 ohms, that's fine as well. And unfortunately, I just had the cap that I took out of the board of that value. It tested the same, but I've already dropped it on the floor, I think, and it's gone now. But what I can tell you is all 3 of the caps that came out of this board don't seem to have an issue. So I think that corrosion is from something else. Maybe it dripped down the write protect LED, like from wet floppy disks or something. I'm not sure. The new capacitors are in. I'm just going to eat away at the corrosion, and I'm just going to cover that with solder. All right, there we go. It's ugly, but I've reinforced it. I just used one of the offcuts from the capacitors, and I went over that area. So that means that the ground connection over here is nice and solid now. I took a closer look at the various connections to resistors, things like that, and I could see some were looking not great, but nothing looked absolutely horrible. But with that said, I'll just reflow this stuff anyways. Can't hurt. At least the larger components, the through-hole components. Definitely the solder connections are looking a little oxidized under here. Could be from the cigarette smoke. Be careful when you do this type of work, you don't bridge any connections. Looks like I did just that in that spot. Okay, well, I think that's all there is to really do on the underside. I'm just gonna put this thing back together and we can maybe do some final testing. There's probably some people watching this who are saying that I probably should have run this thing first before I did any of this work to see if this thing was malfunctioning before I started any of this work after it was sitting all night. Well, unfortunately, when you have intermittent problems like this, there are a few different ways to approach it, and I don't know, this is the way I ended up going. Maybe this was the wrong path, but we definitely saw there was corrosion underneath there, and whether it came from the caps or not, I don't know. Okay, before we put this thing back on, just make sure that this is free of any debris, any little bits of metal or anything else. Now, unfortunately, I only have one of these little screws to hold this on, but I think that should be enough. And that's because there's still a little bit left on those other two things I drilled out that sort of hold this in place. Yeah, that's pretty firmly on there. I went ahead and soldered on 3 wires here for us to probe the drive signatures. And let me get set up with the 4-channel oscilloscope. 3 phases from the motor are on the first 3 channels. I have it AC coupled. They're all lined up here, so it should appear there. And then this bottom trace is this probe here, so we can probe around and look for things like the motor signal. And let's turn it all on. I think this should work. Oh, I broke the disk drive completely, which is quite possible. Well, it sounds horrible, but there was our drive signature. Why is it making terrible clicking noises? Oh, I think the cables were brushing up against it. Let's move those out of the way. There it is. There's our drive signature, looking good. All right, so this blue trace is now set to 1 volt per division. If I type DIR, there we go. It goes up there. Okay, well, the bad thing is it's not misbehaving. Maybe I fixed it. I don't know. Let's run IMD and figure that out. It sounds like it's working perfectly right now. And it is. I'll turn off the beep. There's our 3-phase drive signature. And if I slow it down, the amplitude goes up, as would be expected, right? So while this is running, I'm just taking a look at things. So this is the U phase Hall input, plus and minus. This is the blue trace, and doesn't look like it's doing anything, to be honest. But the drive is obviously running, and it's running at the right speed. Whoops. So shorting out pins together caused it to misbehave. Well, this is pin 30, the speed select pin. This is 29, oscillator input. That's oscillator output, so both to do with the oscillator. This is the discriminator output signal. This is the one we were looking at yesterday. There, turn up the intensity. So this is that signal that goes high when the drive is going too slow, or no, too fast, and goes low when the drive is going too slow. So if I do this, see how it really stretches the signal as it tries to get the drive running at the right speed. So that's completely as expected. So everything, as you can see, appears to be operating perfectly. If I stop the motor, it figures it out and starts spinning it again. Now we're AC coupled on the oscilloscope, so that's why they all just sort of converge into a line in the middle. That is the AC coupling doing that. Because obviously one of these is going to be high, one of those is going to be low to get the motor to start spinning. Well, I think what I'm going to do is I have this probe stuck into the resistor that is the control signal, that's the blue trace. I'm just going to leave this here and let it record for a while, and I'll come back and I can review the footage to see if there's anything happening with the control signal, like if it goes low or whatever, or anything happens with the drive signature to the motor. This thing's been running for quite a while. See if the chip is even warm. Yeah, chip's pretty warm, but there hasn't been a single issue with the disk drive. So I guess that means I fixed the problem by taking the board off and reflowing those joints and replacing those caps and fixing that corrosion. I'm really kicking myself now for not doing what we're doing right now, trying to see those waveforms when it was messing up before I touched it, because it feels like I've blown my chance to see those waveforms in a messed up fashion. So right now, with this is spinning, everything seems to be working. One thing we can't tell easily with just by looking at this is how fast this is running. Well, some disk drives actually have this pattern on the bottom, which is very similar to what you might see on turntables. And I took a picture of another floppy drive, a Toshiba, that had this pattern on it. And I think I can just cut this out, stick it on here, and we should be able to tell how fast this is going. Okay, let's see what happens if I type dir. Oh, it works. It freaking works. So the outside one is 60 Hertz, and the drive I took this off of was also a 360K disk drive. So I just repositioned it. So even though my positioning isn't perfect, we can see that those lines are not moving when I type dir. And that's because the lights in my lab here have a bit of a flicker at 60 Hertz. And of course, if you're in 50 Hertz country, it's that inner circle. But that pretty much tells us right there, this thing is working. I'll upload the JPEG that I took of this to my GitHub repo, and I'll link it in the description below so you can print one of these out for yourself if you want to stick one of these on your 300 RPM disk drives. Well, that is going to be it for this repair video. Pretty anticlimactic, I have to say. On my little post-it note, I wrote bad caps, and I was like, nope. But I mean, these three little tiny capacitors I took off the board, they didn't seem to be bad when I tested them, but there was corrosion on the bottom board there. And whether that came from the caps or not, I don't know. It might have. It certainly was right next to where these capacitors are, so it's entirely possible. But as for what exactly fixed this disk drive, was it reflowing the joints? Was it the capacitors? Was it just taking this off and putting it back on? I honestly couldn't tell you. And I hate these kinds of fixes because I don't feel satisfied that we didn't find something that was, yep, that's the problem, now it's gonna work. It just felt like I was doing a whole lot of guessing and throwing the parts cannon at the drive. I mean, even though I didn't replace any parts except for the 3 caps, still, I just didn't find anything that says this is what's wrong, and that is not satisfactory to me. But on the other hand, the disk drive does appear to work now, so that's a win. And unfortunately, with these types of mechanical issues, that's just sometimes how it goes. So if you found anything interesting about this video, I'd appreciate a thumbs up. But if you didn't, you know what to do. Huge thanks to my supporters. Names are going off the side of the screen. They make it possible I do this full time. You can become a supporter. There are links down below. And you know all the other YouTube junk, thumbs up, subscribe, all the other junk. And that's going to be that. So stay healthy, stay safe. I'll see you next time. Bye-bye.